In this video we talk about the integral test. In the previous video we learned how to find sum of a geometric series, telescoping series, and some other series. In general, it's difficult to find the sum of a given series, so we will use several tests to determine if a series is convergent or divergent without explicitly finding the sum. The first test that we will learn is the integral test. So the integral test says that if the function is f of x is continuous, and we mean by the function f of x, I should show you what I mean by the function f of x. If we are given some series a sub n, and from 1 to infinity, for example, then this term, the general term, is called the function f of n, because this may be given by 1 over n. So f of n will be 1 over n. And here we use x just to, we change the variable because we want to write it in more familiar form. So the familiar variable is the x. So we just write it, replace n with x. So f of x is continuous, f of x is positive, and f of x is decreasing on some interval a to infinity. And in many cases, maybe in most of the cases, a is 1. So 1 to infinity. But if these conditions are satisfied, for example, for values of x that are greater than 3, then we write 3 to infinity, and so on. Now the series under study, the series a sub n, is convergent if and only if the improper integral is convergent. So the series is convergent if the improper integral is convergent, and if the improper integral is convergent, that means the series is convergent. So this test is called the integral test. Now it's very important to note that it's not true that the series converges to the value of the integral. So if the improper integral gives us a value like 1, that does not mean the series converges to 1. Now let's take some examples. The first example is to determine whether the series n from 1 to infinity, 1 over n squared plus 1, is convergent or divergent. So to do this problem, we want to apply this test, the integral test. So the first condition is that now this is f of x. Now this is f of n, so we can write f of x as 1 over x squared plus 1. So the first thing, f of x is continuous on some interval like 1 to infinity. This is the common interval, the most common one. And the second condition is that f of x is positive on this interval 1 to infinity. Now it's continuous because we don't have any problem with this function. If we substitute any value for x, the function is still defined. So, and we don't have any jump discontinuity or any type of discontinuities like jump discontinuity or removable and other types of discontinuity, infinite discontinuity, for example. So this is, we don't have any problem with this function on this interval 1 to infinity. So it's continuous. F of x is positive. You can substitute any value from this interval 1 to infinity, and you find that f of x gives a positive value. The third condition is that f of x is decreasing. You can test this by two ways. The first method or way is that you substitute some values of x here and see the pattern. So for example, you substitute 1, you get 1 over 1 squared plus 1. And then you get, when you substitute x equals 2, you get 1/5. And then substitute 3, you get 1/10. And so on. So as you can see, the series is decreasing on the interval 1 to infinity. Now these three conditions are satisfied. Now we need to apply the integral test, I mean to find the improper integral. Now the improper integral from 1 to infinity of f of x is 1 over x squared plus 1 dx. Now we have a problem here, so it's improper because of the infinity here. So we write limit b goes to infinity, the integral from 1 to b, 1 over x squared plus 1 dx. But we know that this integral is tan inverse of x. Now from 1 to b, and we have the limit b goes to infinity. Now substitute b, you get tan inverse b minus substitute 1, you get tan inverse of 1. But tan inverse of 1 is, what is the angle whose tangent is 1? Pi over 4. And tan inverse of infinity, what is the angle whose tan is infinity? It's pi over 2 in the first quadrant, from 0 to pi over 2. So this is pi over 2. Now after finding this, we notice that the improper integral is convergent. Improper integral is convergent because this is less than infinity. So the series a sub n from 1 to infinity is convergent. And a sub n is 1 over n squared plus 1. Now, if we can't determine that the function is decreasing by plugging some values, as we did here, we can find the derivative. If we find the derivative of the function and we find that the derivative is less than 0 on some interval a to infinity, then that means the function is decreasing. So decreasing means derivative is less than 0. Now let's take another example. This example is well-known example. It's called P series. The series is given by 1 over n to the power p, n from 1 to infinity. And here we have two cases. If p is greater than 1, then the series is convergent. If p is less than or equal to 1, then it's divergent. Now let's take some examples. For example, the series 1 over n squared, n from 1 to infinity. Now p in this case, this is written in the form 1 over n to the power p. P is equal to 2. Since 2 is greater than 1, that means it's convergent. If we want to show this, we apply the conditions, the three conditions, and then the improper integral test. So the first condition, f of x, which is 1 over x squared, is continuous on the interval 1 to infinity. And second, f of x 1 over x squared is positive. As we can see, the denominator is squared and the numerator is positive, so it's positive. 3, f of x is decreasing by just testing some values at x equals 1, x equals 2, x equals 3, or n equals 1, n equals 2, n equals 3, and so on. So this function f of x is decreasing on the interval 1 to infinity, because if we substitute x equals 1, we get 1, and if we substitute x equals 2, we get 1 over 2 squared, which is 1/4, and so on. As we can see, the sequence is decreasing. Now we apply the improper integral. It's integral from 1 to infinity of 1 over x squared dx. This is the integral from 1 to b, limit as b goes to infinity, of 1 over x squared dx. We can bring this up here and find this integral. So this is limit -1 over x from 1 to b. Now substitute b, you get -1 over b, minus substitute 1, you get -1 over 1. Now substitute infinity, you get 0 here, and 1. That's the value of the improper integral. So the improper integral is convergent. That means the series 1 over n squared is convergent. Now we have another example here. If we are given the series 1 over n to 1/3, n from 1 to infinity, as we can see here, p is equal to 1/3, and that's less than 1. Since it's less than 1, the series is divergent, because it's p series. It's a good idea to write the reason here why it's divergent, and here as well, p series. Okay, now let's take another example. Our last example in this video is the sum n from 1 to infinity, ln natural log of n over n. We want to determine if this is convergent or divergent. Now first we write the function f of x equals natural log x over x. The first condition is that f is continuous on the interval a infinity, and this is true. This is continuous for any value greater than, for example, 1. Second, f is, because the problem here happens when x equals 0, or when the values of x are negative or 0. So because natural log or logs are defined for positive values. Okay, so for on this interval 1 to infinity, we don't have any problem. Now f of x is positive on the interval 1 to infinity, because we can try some values like 1. If you substitute 1, you get ln 1 over 1. Natural log of 1 is 0. And then substitute, for example, e, you get ln e is 1 over e. 1 over e still positive. And as you can see, if you substitute any value greater than 1, you get positive, because natural log can be, if we graph it, the graph looks like this. It's positive for any value greater than 1, and x in the denominator is positive for any value greater than 1, and actually for any value greater than 0. So we don't have any problem here with this condition. F is positive on the interval 1 to infinity. Now the third condition, f is decreasing. Here we don't know if this is true. We need to check. We need to check if this is decreasing. If we substitute some values, that need not give us a good indication that the function is decreasing. So if we see such function, this function natural log n over n, and it's not easy to determine whether it's increasing or decreasing, I mean decreasing or not, then we apply the derivative. So f of x equals natural log of x over x. Now we find the derivative. What is derivative of this function? Derivative is the denominator. This is, we apply the quotient rule. Denominator times derivative of the numerator minus the numerator times derivative of the denominator over the denominator squared. And that is 1 minus natural log x over x squared. Now this is less than 0 only if the numerator is less than 0, because the denominator is always positive. This is positive, always positive for values greater than 0. But the numerator can be positive and or negative. So let's solve for x to determine the domain where the function is, where the derivative is less than 0. So we solve this. Let's bring this to the right hand side. We get positive natural log. Now take e of both sides. Now this becomes x and this is e. So f prime is less than 0 for x greater than e. Since x is greater than e, we need to modify these intervals. We can write this. If we leave it as 1 to infinity, that's okay because e is included. So, but for the third condition, we should write it as f is decreasing on e to infinity. Okay, now we apply the integral. So the integral is e to infinity, the improper integral of the function natural log x over x dx. We need to find this integral. This is improper because of the infinity on the limit of the integral. The upper limit of the integral is infinity. So it's indefinite integral here. So we have limit as b goes to infinity from e, integral from e to b, natural log x over x dx. Okay, now we find this integral. As we can see, there is a relationship between the numerator, between natural log and the other function 1 over x. If we differentiate natural log, we get 1 over x, and that means we can apply a substitution method. U is natural log, then du is 1 over x dx. That means dx is x du. Now we change the limits of the integral. When x is e, u is natural log of e, and that's equal to 1. When x equals b, then u equals natural log of b. And then we can find the improper integral limit as b goes to infinity, the integral from 1 to natural log b of u. Now ln of x is u over x times dx. dx is x du, and then we cancel x and we integrate. So this is limit b goes to infinity, u squared over 2 from 1 to natural log b. This is limit b goes to infinity, natural log b squared over 2 minus natural log, minus 1. We substitute 1 here. So 1 squared over 2. Now substitute infinity. You get infinity, natural log of infinity is infinity, squared over 2, still infinity, minus 1/2, and that's infinity. So since the improper integral is divergent, that means the series natural log n over n from 1 to infinity is divergent.